This is the third episode of a series where we together implement a library for runtime immutability checks called imcheck. And I wanted to change the format a little bit, and I decided to make a bunch of changes offline and then record a short summary of what I have right now and guide you through the most important changes. Hopefully it will create like a shorter videos that will be as relevant and as interesting as the previous one. So this is our library in a current state. I spent like a few hours working on it from our previous state. So for that, for the previous changes, you can check our previous videos. And let's quickly look through what we have here. So we have this library that helps us to detect mutations on variables and different structures that we want to remain immutable. So how exactly it works? So let's imagine that we create a variable of any type, basically. We change it somehow, and then at some point we want to declare that we want this variable to be immutable from now on. And for that we use ensure immutability call. This ensure immutability call will return us a function, and this function is required to evaluate if value remained immutable or not. So in our case, we could call it whenever we wanted, but in our case, we decided to defer it to the end of this function. And let's imagine that I will remove this mutation and run this test. And we will see that mutation is not detected. Okay, and if I start to mutate it, we will get a panic and the problem that describes what happened where we captured an immutable snapshot and where we detected that it was mutated, and a bunch of additional data that will help you to debug and understand what actually happened. So we'll maybe revisit this test later on, but let's check what actually changed since I started to work on it offline. So this is the diff of all changes that I made. So you can see the first thing is that we now don't need this main because I've created a bunch of tests for our library, so we don't need this thing now. And the most significant change that is apparent right away is that previously we used a map of uint pointer to uint64 for checksums, capture, and comparison. Now we are using a little bit different thing. We're using a structure that has the same kind of uint pointer, but also it has this reflect kind type, which is simple uint with the following possible values. And why do we need this thing at all? Because pointer is the pointer, and why do we need to understand in different contexts and have like separate checksums for separate contexts of the same pointer? So the reason is it's kind of a bug that I detected while I was implementing the whole thing. So apparently, let's say in a complex examples where we have, let's say here. So here we have like a structure. Every structure has some age and then some separate pointer to the similar structure, to the same structure. And let's imagine that we have a slice of such structures. In that case, we gonna have the same value of a pointer for different checksums, because what we want to do when we capture this checksums map, we want to capture a checksum for the whole slice, but then we want to capture a checksum for separate substructures or like structures inside the slice. And then potentially we also want to capture a checksum for every field of every structure. So sometimes we can have like multiple values with the same pointer, but at sometimes we want to interpret this pointer as a pointer to the whole slice of the structures, and sometimes we want to interpret this pointer as a pointer to the one structure. So if we run this test right away, you'll see that we have in our checksum map, we have a bunch of checksums, and some of them are kind of the same. So if we look, you can see that this pointer is present in our structure 2 times. It has different checksums and it has different kinds. And if we go and check the kinds, you will see that 23 corresponds to, I believe, yeah, for slice. So in that case, we kind of capture the checksum for the whole slice with 2 structures inside. That's why we have this checksum. And then we interpret the same pointer, but as a checksum only for one struct. 25, it's a struct. And then we gonna have this checksum. It's for the second struct in this slice, and these 22s, it's for these pointers. So yeah, that's why we need. This is like one of the most significant changes that I made. Okay, let's take a look what else changed. So now I started to capture a stack trace where the snapshot was captured. And this actually helps us a lot to understand what happened. So once again, if we go back to our tests, you can now see that, okay, this test failed for some reason. Okay, or no, it's not failed, but I'm just adding this. I'm adding these messages that I captured to a test log, so I can then read them and show it to you. But let's say, okay, so we detected some mutation of immutable value detected, and then we show you where exactly we captured the snapshot of this value, and then we show you where we detected the mutation. And we can see that this is like at the end of this function. That's because we are evaluating these mutations and checking for mutations in defer. That's why it's in the end of this function. Yeah. So we are using this information from a stack trace to understand where we capture different snapshots. It's kind of a little bit expensive, but as we mentioned before, we wanted this library to be sometimes hidden behind the build flag. So if you're kind of worried about potential potential overhead, we can remove it. We can also have like a separate flag that, for example, just not capturing stack traces. Yeah. For that thing, yeah, we can just skip and not fill in these 2 fields. And when we print this information, we can check if this field is not present. Okay, we're gonna skip this line and so on. Okay, what else? I think you can also notice that I added 2 like external dependencies. They're actually optional because the functionality of this library not going to change at all if we remove these two libraries, but the user experience, they help a lot with user experience. I'm using this spew library to capture these beautiful like string representations of our snapshots. So you can easily understand what is happening, what's the type of every structure, and so on. And then I'm kind of capturing these string snapshots, and then I'm using the other library called div or godiv, godiv, to show you like a beautiful human interpretable div that shows what exactly changed. So it's a lot easier to debug any mutability failure. We can also hide these things behind build flag, or we can skip the capture of these things if we want to. So yeah, we will see. I think we're gonna have a benchmarks, and then we will see what is the overhead of all these beautiful things that we have here. Okay, what else? As you can see, I started to add a bunch of to-dos. Since we have a huge gaps between different episodes, sometimes I can forget some ideas, and these to-do statements all over the place will potentially help me to remember what I wanted to do as well. Okay, and let's check what other things changed. Apart from the things that I described, not very much changed. I just added a support for more different types. So now we kind of have support for arrays, slices, and strings. They have almost the same, they're kind of almost the same, but not exactly the same, because for reflect, slice, and string, I can easily kind of cast this slice of any type to a slice of, or string, to a slice of bytes. Sorry, if you hear any noise, it's actually a rain outside, and I don't think I can change anything about it. So yeah, we kind of have additional sound effects here. Yeah, so what I'm actually doing, I'm using unsafe, and I interpret this pointer to this slice as a slice header, and then I evaluate what is the size of the type of this slice, and then I interpret the whole thing as a byte slice, and I capture a checksum for the whole byte slice of any type that we have. But for array, we can't do the same thing because array has no slice header. So we actually create a slice header for this array. So we say, okay, like we have a pointer to this array, and we say this is the pointer to the data, and then we kind of create length and capacity for it, and then we do literally the same thing that we do for slices and strings. So the way how we create this slice header is a little bit different, but almost everything else is the same. So maybe in the future I will kind of refactor this code a little bit and merge them together. We'll see. Yeah, I think it's possible. We will just change it a little bit, but let's do it somewhere in the future, because maybe we're gonna find some other like similar types, so we can do it later on. We also now support structs, so we kind of now support a bunch of nested fields and structs and other things. And I also added the support for structs. We actually do almost the same thing as for slices, but instead of we kind of interpret one struct as also as a byte slice, and we capture the raw checksum of this byte slice. And let's check what we do as well now when we have, for example, a slice of complex structures. What I'm doing actually, so I'm capturing the checksum of the whole slice, and then I'm capturing checksum for every for every item within this slice. So this is the thing that happens here, slice or array snapshot. And here, as you can see, I'm checking the length of this value, and then I check if it's a primitive value or not. And if it's not a primitive value, I'm kind of I go and evaluate checksum for every item in our slice or array. And what is primitive values? So, and why don't we capture checksums for them? We don't capture checksums for primitive values just because they can change, or they can change, but we're going to detect this change by our previous row by slice checksum. So we kind of check that if our value is one of those, it means that we will detect the change just by using our previous checksum. And if our value is struct, then we check if all the fields of this struct are also primitive. And that's it. So we basically, for example, I don't think we have actually examples of such structs here, because this primitive struct, it has the pointer to the person. So the thing is, it's not actually as primitive. So what if we do, we need to change it maybe a little bit. Let me think about it. Maybe we can change this test to have, I don't know, some other primitive value. Age, and then let's have something else. Age and height, and it's gonna be int 8, let's say. Why not? Still gonna work, hopefully. Yes, and as you can see, despite the thing that we have multiple fields in this array, or in this slice, and we have two structures within this slice, we have only one checksum for the whole thing. And it's just because we have a slice of primitive values, and we don't need to check anything else, because as soon as we change one of those, we will be able to capture, to understand that something changed. Okay, so for structures we do almost the same thing, but for let me see, for structures we capture the row checksum, and then we go through all fields and we check if our field is not primitive, we will capture the checksum for this non-primitive field. But if everything is primitive, we don't need to do anything else. We can also have this kind of the same test, but only for checksums, only for structs. So if we say, okay, I don't have I have just a struct of person, and we have age 13 and height is 150, let's say. And let's imagine that we want to capture immutability of this thing, and then we change it a little bit. So we set age 0. Test primitive structs, or primitive struct. This thing should fail, and yes, it fails, and it shows where it detects any change. once again, we show where exactly we captured the snapshot, and we show where we detected that something went wrong. Okay, so it works. What else do we have here? Yeah, we support a bunch of primitive values. So for example, even for such thing as a counter, as I showed you before, we have just counter of Uint64. We can change if it's mutable or not. And for now, not supported types for us are like channel function interface map and unsafe pointer. I think we can do it later on in some other episodes. The only thing that I'm not sure about is, let's say, unsafe pointer. So we can kind of capture unsafe pointer, but we don't know what it points to. So we can't evaluate immutability of such pointer entirely. So what we can do, I thought maybe we can have like different variants of this routine that can, for example, disallow unsafe pointers. So if you try to capture immutability, if you try to ensure immutability of some value that has unsafe pointers inside, we can panic right away. Yeah, not sure about that. We can have both. We can have it both ways. The same for channels. Kind of channels are created to be mutable to some extent, so it's kind of hard to check if they're mutable or not. What we can do, we can check the channel is closed, for example. So you can make something immutable, and then, yeah, if you want to verify that something is immutable, your channel inside this something should be closed. That's one thing that I thought can be useful or possible. We'll see. What else? And I think that's it, more or less. Yeah, we can also check what is, with all these changes that I made, what is now possible. So we have these counters, I showed it to you. The slice of integers, not very interesting. Floats, it was working before as well. So this thing we just added, we kind of went through those. Let's take a look maybe on this one, where we have a slice of structure and we have a string there. So as you can see, and we kind of replace age. We can also change maybe name. So let's say we change name to second, and if we run it, you'll see that yeah, we now have, we detected this change, and here we show what actually is changed. So you can see that we had string, now the length is a little bit bigger, and it is second. And let's check that thing that is actually oh, I had similar check in the nested kind of thing. So let's say we have person struct, and it has a pointer to the parent struct, and we can see that, for example, we have grandparent, then we have parent that points to grandparent, and then we have 3 kids that all 3 are pointing to parent. And then we kind of capture immutability, or want to ensure immutability of this struct. So, and then we change a name of grandparent, and let's check what we're gonna get here. As you can see, we can see that we managed to detect the change, and you can see in 3 cases we kind of show that length didn't change in that case, but we detected some changes. Yeah, and let's check the last test case. That is, I think, the most interesting, especially for people that are using unsafe a lot. So let's imagine that we are kind of want to, I don't know, reduce allocations, and we sometimes cast byte slice to string right away. So I thought at first, why do we need to capture string checksums? Because strings are kind of immutable. So all we need to do is just like capture maybe pointer and length or something like that, and that should be it. Or just pointer. Yeah, better pointer and lengths. And that's it. But then I thought, okay, in many cases in the high performance code, we tend to like to sometimes to reduce allocations. We sometimes use unsafe code and directly cast byte slice to strings. So we kind of have now immutable string, but it points to a memory on heap, and this memory is actually mutable. And if you have some other thing, if you're using unsafe, you can actually mutate this memory, and we won't be able to detect it. So I didn't want our library to be as bad. So I thought, okay, we can actually, yeah, we will need to evaluate checksums for strings as well. And then this thing is now possible. So we have grandparent name bytes. We use this grandparent name, we cast it through unsafe to string, then we create almost the same structure as we had here, but now we kind of change the byte slice that we used for grandparent name, and we still will be, we still can check that underlying byte slice changed. So it also works. Okay, I think that's it for today. I will post all these changes to a separate pull request and separate branch on our GitHub repository, and I'll post the GitHub repository link under the video as well. So thank you everyone, and see you around. Bye.